before the exam. So on Tuesday, we started second order linear. ODE, ordinary differential equations. So the general form of a second order linear ODE that we could hope or attempt to solve would be something that looks like y double prime plus p of t y prime plus q of t y is equal to g of t, right? This would be what we would call a second order linear ordinary differential equation. We're allowed to have functions of t as coefficients of the y double prime, y prime, and y, and of 1 essentially, but nothing else. And what we discussed, or what we found, is that first of all, going to second order immediately leads to more challenges than we saw in first order. So we started working with the most simple possible case. So what are the two conditions that we put on this second order ordinary linear differential equation before we could find actual solutions? I know it's a couple days ago, but what simplifications did we make to this equation? Or what assumptions did we make?
Assume that g of t was 0?
Yes. First, we assume that g of t was 0. And what is this assumption called?
It's homogeneous.
Yes, this is homogeneous. So a homogeneous linear differential equation is when you only have coefficients in front of functions of y with no extra term at the end. And then the second, so this is the first simplification we made. What's the second simplification we made?
We assume P of T and Q of T were constants.
Exactly. We said P of T is going to be equal to P, a constant, and Q of T is equal to Q, which is a constant. So these are like really, really severe simplifications, like drastic simplifications that we made before we could actually get solutions to this differential equation. Okay, and then what are the things that we found? Well, I'll start us off. One thing that we found is that we expect e to the RT to be a solution, right? For some r. And what r is supposed to be a solution? What r is supposed to make this work?
R being that polynomial AR squared plus BR plus C.
Exactly. So in this case, it's a little different, but when R is a root of the characteristic polynomial. And if we have AY double prime plus BY prime plus CY being equal to 0, then the characteristic polynomial is just AX squared plus BX plus C being equal to 0. So as long as R is a root of this polynomial, then we found that e to the RT is a solution to this homogeneous second order linear differential equation. So first of all, this is telling us a couple things. One thing is that for second order linear ODE, you should keep in your mind exponential functions as the you know, for the solution to the most basic ones, exponential solutions are popping up as solutions. So what are the possible cases for the factorization of this second order polynomial? What are the possible roots of a degree 2 polynomial?
Just be the quadratic formula.
Yes, it's just a quadratic formula, so we can always find two roots of the second order or degree 2 polynomial. But it turns out that there are kind of some different situations that end up being important. Maybe I'll write this out. So the first possibility when we factor it is that we have two real distinct roots. But what other scenarios could possibly occur?
We could have one real root or like complex imaginary roots.
Perfect, yes. So if we have one real root, then the point is that it appears twice. So we could call this of order 2, or repeated, right? We'd have a repeated real root. Or we could have two complex roots. And there's an important theorem that you should remember, which is if we have two complex roots that are the roots of a degree 2 equation over the reals, what information do we know about those complex roots? Can they be anything? Can I have two totally random complex numbers be the roots of a degree 2 polynomial with coefficients in the reals?
They have to be like conjugate.
Mm-hmm. The complex numbers must be conjugate to each other. The roots are complex conjugates. Okay. Let's see. So, and probably it's a good idea to think about why this holds, right? So if you write, let me just do as an aside. If we take x minus a plus bi times x minus c plus di. So here I'm saying I've got a polynomial with two complex roots. And then if I FOIL, then what I'm going to get is I'm going to get x squared minus a plus bi plus c plus di, right? This is what I'm going to get out of the second term. We get minus one of these times x, minus one of these times x. And then lastly, I'm going to get plus, and here I'm going to get ac plus ADI plus BCI minus BD. Do we agree how I foiled this? Is this okay?
Yes.
So the condition that this number n and this number m, n and m are both real forces a plus bi and c plus di to be complex conjugates. I'm just reinforcing the idea that this notion of the two real roots being complex conjugates isn't something that you have to memorize. It's something that you can see very explicitly. You just have to check, well, if a plus bi plus c plus di is real, that means b has to be equal to negative d. And then over here, if I need the I coefficients to vanish, because I want m to be real, then I know that AD plus BC also has to be 0. And yeah, so what you'll find is that these are exactly the conditions that A plus BI and C plus DI are complex conjugates. Okay, so this is a bit of a digression, but the point is we're going to examine these two cases more carefully later. What we really dealt with was the first case. When we have two real roots, say R1 and R2, then what we were able to do is we were able to build a two-dimensional family of solutions, of general solutions, which looks like C1, so y is equal to C1 e to the R1t plus C2 e to the R2t. So some things that I want to kind of reinforce here is that even though we're dealing with very simple behavior, right? We only really solve this for very, very simple second order linear differential equations, but the features that we see in the nicest examples of these cases are kind of, they give us guides for what we should demand or what we should try to find for a general second order linear equation. In particular, a really important point that we're going to deal with a lot today is we want to have a family of solutions that depends on two variables, right? Like this. This should be what we ask of second order linear solutions. We should ask for a family of solutions depending on two parameters. Okay, so this is just kind of an overview of the stuff that we discussed 2 days ago, but it's important material to kind of understand what the patterns are that we're going to be looking for. Any questions on this review of the first section of chapter 3? This is all clear. This is all straightforward.
Yep, all good.
Okay, cool. So we got into the very beginnings of section 2. So what we did in 3.2 is the first thing that we did is we introduced linear operator notation. And then the real point of 3.2 is the following. In 3.1, we looked at the most simple and the most basic second order linear homogeneous differential equations, and we saw a certain behavior. Namely, we expect two-dimensional families of solutions. And now the next question, and the one that 3.2 examines, is how generally does that fact hold? When can we find, like, maybe I'll write some questions. Are solutions to IVPs with first or second order linear homogeneous diffuse unique? Do they exist? Is the general solution of the form C1y1 plus C2y2 for some solutions y1 and y2. And here, here's just one place where we can start using the linear operator notation. Now I can write what it means to be a solution if L is equal to d squared plus p of t times d plus q of t. Then this is an operation which takes a function. Now L of phi is going to be equal to second derivative of phi plus p of t times the first derivative of phi plus q of t times phi. And now I can just ask, when is L of phi equal to 0? So now, what does it mean to be a solution? It means that you are killed by this operator L. A solution to the differential equation. Okay, so is this all right?
Can you just to clarify, if you can get L of phi to be 0, then that means whatever phi you put in is a solution for the differential equation?
What I'm saying is that L takes a function and gives you back a function. And if L takes some function phi and gives you back 0, that's equivalent to that function phi being a solution to the differential equation that's represented by L, right? When I write L is equal to d squared plus p of t times d plus q of t, I can think of this as representing a differential equation because it tells you how you're supposed to differentiate a function. And if I differentiate a function phi in this way and I get back 0, that's the same thing as phi being a solution to the differential equation.
Okay, thank you, that makes sense.
Does that help? Yeah, like we can do an honest, like, if I write some explicit differential operator, like L is equal to d squared plus 2d, then what this means is L of some function f is equal to f double prime plus 2 times f prime. It's just telling you exactly what process to apply to the function. And then if this is equal to 0, then f satisfies the diffie q of f double prime plus 2f prime is equal to 0, right? It's really mostly a notational thing right now. So we'll write if L of f is equal to 0, then f satisfies this differential equation. Okay, and then what we started discussing were these theorems of existence and uniqueness. So first of all, can someone tell me what I should expect in terms of initial data or an IVP in the second order linear homogeneous equation, in the second order linear homogeneous realm, so to speak?
You should expect 2 pieces of information, one where you have it for the original function y, and one with the first derivative of y.
Exactly. I expect data about some value that the function has, and also the data of the derivative at that particular point. So we have the following theorem. So consider the IVP, which is given by y double prime plus p of t y prime plus q of t y is equal to 0. And the initial data, y of t0 is equal to y0, and y prime of t0, the derivative at this time t0, is equal to y prime of 0. So we're given, at a certain point, a position of the function and its derivative. Assume that p, this should be g of t. We're doing something a little more general here, not just dealing with homogeneous differential equations. Here's a question. What does it mean to be a solution to this differential equation in terms of the differential operator L? If L is d squared plus p of t d plus q of t, what does it mean to solve this differential equation?
Could you say that again?
Right. So you know what it means for a function to satisfy this differential equation. And that is, I take some function y, and I take a second derivative, plus p of ty prime plus q of ty, and I check whether that's equal to this given function g of t. But now we're introducing this differential operator notation of L, like applying this operator to functions f, where applying the differential operator is taking the second derivative, adding the function p of t times the derivative plus q of t. So I'm just asking, up here, if I had a homogeneous differential equation, I could say phi is a solution if L of phi is equal to 0. What would I write here for a solution to this differential equation?
If L is equal to g of t.
L of phi being equal to g of t, right? So here in a box, I'll put phi is a solution if and only if L of phi is equal to g of t. So this is kind of a compact way of writing the differential equation for this particular L. Okay, not really pertinent. I mean, it's a notation that becomes important, but I don't want to harp on about it right now. Okay, so we're in the middle of a theorem. Assume P, Q, and G are continuous on an interval L, or sorry, an interval I containing T0. Can anyone have a guess what we should expect? Actually, it's not a guess because I told you last time, but can anyone tell me what I get here in terms of existence and uniqueness?
It exists within the interval, but you can't extend it any farther than what of the function lies in continuous in the.
Yes, so then there exists, that's a terrible there, that looks awful. There, it's worse, exists a unique solution to the IVP, and it is defined on all of I. So I take a little umbrage with your statement that it can't be extended. You're right in the sense that we can't extend the solution past the points where P, Q, and G are continuous. However, we can extend our solution exactly that far. Like we can extend it the most that we could possibly hope for, just depending on P, Q, and G. And I want to kind of contrast that behavior with the existence and uniqueness theorem for nonlinear things. For nonlinear stuff, there exists a smaller interval I prime contained in I where you have a solution, and maybe you can't extend it to all of I. But here, we can extend it to the biggest possible interval on which P, Q, and G are all continuous. Okay, so the proof of this theorem is beyond the scope of our class. So proof requires more analysis. So we're essentially just going to use this theorem. But this tells us that essentially, in terms of this, in terms of what we expect from solutions to second-order linear ODE, their solutions and existence and uniqueness and how far you can extend them is basically the same as for first-order linear. In other words, it's kind of the nicest possible behavior that you could possibly expect. Let's try some exercises where, on which intervals are solutions defined for the following IVPs. Let's first consider y double prime plus cosine of t y prime plus 3 natural log of the absolute value of t y being equal to 0, with the IVP y of 2 is equal to 3 and y prime of 2 is equal to 1. So here's one IVP where I'd like you to find on which domain, or the largest possible domain on which I can have a solution to this one. And then the second one, let's do x minus 2 of y double prime plus y prime plus x minus 2 times tangent of x times y being equal to 0. And with initial data, y of 3 is equal to 1 and y prime of 3 is equal to 2. So why don't you give these a shot for a minute or two. So what's the answer for the first one?
Is it all R because you have the absolute value of the t and the natural log?
Not quite, because natural log of t still can't be defined as a function at 0, right?
Right.
So since we know that natural log of t has a discontinuity at t is equal to 0, what is the largest interval on which we could possibly have a solution?
It'd be like 0 to infinity.
Yeah, here, 0 to infinity for this one. Has anyone finished this one here?
Yep.
Okay, right. So what we first have to do is divide everywhere by x over 2, right? So the coefficient in front of y prime is going to be 1 over x minus 2. Where does that have discontinuities?
X equals to 2.
Yeah, of course. So if I kind of sketch out lines, I've got a problem at x equals 2. And then for tangent, I've got problems at negative pi over 2. I've got problems at pi over 2. Hang on. How does pi over 2 compare with 2? It's less than. Pi over 2. And I've got problems at 3 pi over 2. This shouldn't be here. So from this sketch, what's the interval on which we can define this solution?
Two to 3 pi over 2.
2 inclusive to 3 pi over 2. Exactly, right? 3 is greater than 2, is less than 3 pi over 2, and if we try to go lower than 2, we'll have a discontinuity in one of our functions, and if we try to go higher than 3 pi over 2, we'll have a discontinuity in the other one of our functions. So we can only hope for a solution on this interval. Once again, I want to contrast this behavior with the behavior that we saw for nonlinear. For nonlinear differential equations, we could not predict just from the differential equation where the solution would be defined, and the general idea is it's probably smaller than you hoped, the interval where it's defined. But here we know exactly where it's defined, and it's the biggest possible interval on which all of your functions are continuous. That contains the initial point. Any questions on this? No? Okay. So here is the next very important theorem. This is called the principle of superposition. But I would rather call it the space of solutions, or the set of solutions is a vector space. So can someone remind me what you can do with a vector space? If you have two vectors in a vector space, what are you allowed to do?
Add them and multiply by constant.
Exactly. So what we can do is we can add solutions and multiply by constants. So this is one that I think all of you can quite easily prove. So let L be equal to d squared plus p of t d plus q of t d. Or not d, just plus q of t. Let y1, let L of y1 be equal to 0, and let L of y2 be equal to 0. Then L of c1 y1 plus c2 y2 is equal to 0. Proof. And what I'd like for you to do is to prove this, please. I'll give you a couple minutes. There's not really any idea that's involved with this proof. It's really just following the definitions. Doing all right? Anyone finished?
I think we're good.
Okay, I'll just go through it pretty quickly, but I just wanted you all to give a stab at it because I think it's pretty straightforward. And it just really means unwinding the definitions. So the proof is that L of C1y1 plus C2y2, by definition, is equal to d squared of C1y1 plus C2y2 plus P of t d C1y1 plus C2y2 plus Q of t times C1y1 plus C2y2, where d is the differential operator. What do we know about second derivatives or derivatives is that they split over sums and constants pass through. So this is all equal to C1 times d squared y1 plus C2 times d squared y2 plus P of t C1 d y1 plus P of t C2 d of y2 plus Q of t C1 y1 plus Q of t C2 y2. What is this column?
C1 times L of Y1.
This is just L of y1, right? Yeah, C1 times that. C1 times L of y1, exactly. And this column is exactly C2 L of y2. And by assumption, L of y1 is equal to 0, L of 2 of y0 is equal to 0. So this is all 0. That more or less what everyone had? Okay. I'm just going to assume that the answer is yes. Y'all are some smart people. So we show that for a linear homogeneous differential equation, once you have two solutions, you can add them together, you can subtract them, you can multiply by constants, et cetera, et cetera. So the hope is that we can get general solutions from this. That is, we should try to form a two-dimensional family from our solutions, y1 and y2. So the following questions come up. This was only about solving the differential equation, and it didn't have anything to do with solving the IVP. So we should ask, when can we choose C1 and C2 such that C1y1 plus C2y2 satisfies a given IVP? And the given IVP, of course, is just going to be the data of this differential equation plus the additional data of y1 of, what would it mean if I'm given initial data of y of t0 is equal to y0 and y prime of t0 is equal to y0 prime? Well, if C1y1 plus C2y2 satisfies this initial data, then that's essentially just saying C1 times y1 of t0 plus C2 of y2 of t0 is equal to y0, and I take derivatives. C1 of y1 prime of t0 plus C2 of y2 prime of t0 is equal to y0 prime. right? Do we understand what I'm doing? So I'm saying I'm starting off with two solutions, y1 and y2, to the differential equation, and I'm asking, can I find constants such that these are solutions to a fixed IVP? Is this okay? Yes?
Yeah.
Okay, great. So essentially, what I'm asking here is that how should I describe this? Let me draw R cross R. Here is R cross R. And I'm going to put some random point out here, and this is going to be the data, y0, y0 prime, right? It's just two numbers. The first number is the height of the function at some point, and the second number is the slope of that function at that given point, right? And then over here, I'm going to draw, essentially, it's either a pointer or you can think of it as a vector. Then I'm going to draw two other vectors, like this. Here, this is going to be y1 of t0, y1 prime of t0. And this one is going to be y2 of t0 and y2 prime of t0. So I've got three vectors going on. This vector is the data of the, so this is our solution y1, and we have a number of what is y1 equal to at t0 and what is the derivative of y1 at t0. And then we have the data of what is the value of y2 at t0 and what is the derivative of y2 at time t0. And the question is, can we find a linear combination of these two vectors such that they reach y0 and y0 prime, right? That's exactly what this system of equations is asking. Can I find some constant c1 such that I scale this vector by that constant? And then I find some second constant c2 such that I scale this vector by that second constant, such that I add these vectors together and I get y0, y0 prime. I'm asking, is this vector inside the what's called the span of these two vectors? Is this terminology that I'm using familiar to you when I say this stuff about vectors, or no?
Yeah, it's a little rusty, but yeah.
It's a little rusty, but do you kind of agree that, at least pictorially, when I'm asking whether this linear system has a solution, I can transform it into asking, I take two vectors and a third vector, and I ask, can I reach the third vector by walking along paths given by these two vectors, more or less?
Yeah, that makes sense.
Yeah, right. Okay, so in 2 dimensions, the point is it's kind of easy to understand when the answer is yes. Whenever the two vectors are not scalar multiples of each other, then we'll always be able to get to the third point. So the only time that this kind of fails is when I have two vectors, one that looks like this and one that looks like this. And then say my third point is over here. Can I ever hit this third point by some linear combination of these two vectors?
No.
No, because if I go some distance along the direction of this vector, and then I add some distance along this vector, I'm always going to stay on this line. Whereas if the two vectors are not linear multiples of each other, not scalar multiples of each other, then I will be able to hit this point by some linear combination. And you can kind of think of it as like a parallelogram that has one side parallel to the first vector and another side parallel to the second vector. Okay, so we have important words that we use to describe these two very different situations. here, the two vectors given by y1 prime, and y2 prime are linearly independent. And here, these two vectors are called linearly dependent. And the idea is that these two vectors span the whole plane, whereas these two vectors only span a line. That's the case in 2 dimensions, at least. Are we doing okay? Any questions on what I'm bringing up here? I kind of feel like there should be a question. I don't know what, but.
So you're saying as long as the two solutions aren't linear multiples of each other, we can find a C1 and C2 that satisfy those equations?
Exactly. In the dimension 2 case, what I'm saying is that if the two vectors given by the numbers y1 t0 and y1 prime t0 and y2 t0 and y2 prime t0, as long as these two vectors that are given by the columns are linearly independent, then I can find unique constants C1 and C2 such that this system of equations is satisfied uniquely. On the other hand, if these two columns are linearly dependent, which in this two-dimensional case means that they're scalar multiples of each other, then there will be many points, y0, y0 prime, that can never be reached by any linear combination of these two vectors. And then we can't solve the IVP for many IVPs. Does that make sense?
Mm-hmm.
So I'm saying, and what this discussion works down to is, we can solve a general IVP as long as our solutions have these kind of associated vectors that are linearly independent. So let me now go a little further. Given two vectors, so here's the point. We can solve arbitrary IVPs if, and only if, the vectors, and I'll write it kind of sideways, y1 of t0, y1 prime of t0, and y2 of t0, y2 prime of t0 are linearly independent. This is something that we essentially see from this work and from this discussion. So my question to you is, how can we determine if vectors are linearly independent? I'll give a hint. The first part of it is to arrange them into a matrix. So I'm going to make a matrix that looks like y1 of t0 and y1 prime of t0, and then y2 of t0 and y2 prime of t0. Does anyone know an operation or some number that we can compute from a matrix that will tell me whether these things are linearly independent?
The determinant?
Yes. These two vectors so star, are linearly independent if and only if the determinant of this matrix is equal to 0. So this is, I should probably put this as a theorem. So we can solve arbitrary IVPs with diffq L, where here L is once again d squared plus p of t d plus q of t. I'll just write that. D squared plus p of t d plus q of t. Whenever we have y1 and y2, which are solutions, so L of y1 is equal to L of y2 is equal to 0, and y1 of t det y1 of t 0 and y1 prime of t0, y2 of t0, y2 prime of t0 is not equal to 0. And it'll be sum c1 y1 plus c2 y2, where the c1 and c2 are determined by whatever satisfies this linear system. This particular kind of determinant, this is called the Wronskian of the two solutions. So we'll write W of y1, y2 at t0 to be equal to the determinant of y1, y1 prime, y2, y2 prime, evaluated at t0. Wronskian.
Wait, did you say that the vectors are linearly independent if the determinant is equal to 0 or if it's not?
Not equal to 0. And this is a pretty easy one to check because, so a check. This is easiest in the two-dimensional case, but it generalizes. So what does it mean for two vectors to not be linearly independent? In the two-dimensional case, you can kind of see the only way for two vectors to not be linearly independent is for one to be a scalar multiple of the other, right? So if we have v1, v2, and then cv1, cv2, so we expect these to be not linearly independent. These should be linearly dependent vectors. Well, the determinant of this is equal to c v1, v2 minus c v1, v2 is equal to 0. So here we see if the determinant is 0, or if these things are not linearly independent, then the determinant is 0. And it's true that the other way holds as well, that if it's 0, if the determinant is 0, then these vectors are linearly dependent. So the thing that you want, if you want solutions, is for the determinant to not be 0. Is that clear?
Yeah.
And moreover, if W of y1, y2 at t0 is equal to 0, then there will be IVPs associated to L and y0, y prime of 0, which cannot be satisfied by any C1 y is equal to C1 y1 plus C2 y2. So essentially what I'm telling you is that in general, we want to find two-dimensional families of solutions such that one element of that two-dimensional family will satisfy any arbitrary IVP that you hand me. And what I'm telling you is you can do that so long as you find two solutions which are linearly independent, and the way that you check whether they're linearly independent is by computing their Wronskian. So the first thing that we should do is compute some Wronskians. Before I do that, though, are there any questions? Okay, so let's do some examples. We saw that e to the negative 2t and e to the negative 3t are solutions to y double prime plus 5y prime plus 6y is equal to 0. Find their Wronskian. W of e to the negative 2t, e to the negative 3t.
Wait, should that be a minus 5y prime?
I don't think so. Remember that here these should be the roots, so I'm looking at x minus negative 2 and x minus negative 3, right? And then I get this. In other words, plus 2, plus 2. And indeed, negative 2 and negative 3 are the roots of this. And someone should let me know when you found the Wronskian, and then we can interpret what it's saying to us. let me just get started writing down what I should compute for the Wronskian. The first thing that I should do is I should just find the vector associated to this solution. What's a solution? So I'm going to have e to the negative 2t up here. And then down here, what should I have?
Negative 2 e to the negative.
It's derivative, exactly. Negative 2 e to the negative 2t. And up here, I'll have e to the negative 3t. And down here, I'll have negative 3 e to the negative 3t. And what I'm looking at is the determinant of this thing, which is exactly equal to negative 3 times e to the negative 5t minus negative 2 times e to the negative 5t. If I did this correctly, which should be equal to negative e to the negative 5t. Did everyone get this?
Yep.
Okay, so the thing to recall, so let's kind of go through some of the things that we can think about for this differential equation. First of all, the existence and uniqueness theorem tells us what about the solutions to this differential equation?
Like the interval that it would exist on.
Yeah, so the existence and uniqueness theorem tells us, first of all, that these functions are continuous everywhere. So given any initial data, I can find a unique solution which satisfies that initial data, satisfies this differential equation, and is defined everywhere. So given any y0 prime, there exists a unique solution satisfying this IVP. It is defined everywhere and defined on R. That's what we immediately know from existence and uniqueness. Do we agree?
Yes.
So now the critical question is, well, I've got these two solutions. I know that some solution exists. Is it true that any solution can be written in terms of these two solutions? And the thing is, we check the Wronskian, and the thing that we want to avoid is the Wronskian being 0. Because when the Wronskian is 0 for some t, if there's some t0 that makes the Wronskian 0, then these two solutions don't have linearly independent data at that point. So is this function ever 0?
No.
Negative e, so w of e to the negative 2t, e to the negative 3t is equal to negative e to the negative 5t. This is not 0 for any t0. Thus, given any t0, y of t0, and y prime of t0, this being some totally arbitrary solution to the IVP, where I pick a time, I pick a position of the solution at that time, and I pick the derivative of the solution at that time, given any initial data, then there exist C1 and C2 such that y is equal to C1 e to the negative 2t plus C2 e to the negative 3t satisfies this IVP. In other words, here I am saying for any possible initial data that you could possibly come up with, I will be able to write the solution that satisfies this IVP, which we know exists and is unique by our existence and uniqueness theorem. I'll always be able to write it in terms of my two solutions that I found, e to the negative 2t and e to the negative 3t. in this case, we call these solutions a fundamental system of solutions. So here, e to the negative 2t and e to the negative 3t are a fundamental system of solutions. Because every possible conceivable solution to an IVP can be written in terms of these two solutions. Any questions on this? No? Okay. Y'all are kind of quiet today. That's all right. That's okay. I understand. Okay, where are we going now? Yes. Okay, so maybe I should formalize this in a theorem. Formalize. This is theorem 3.2.4. So suppose L of y is equal to y double prime plus p of t, y prime plus q of t is equal to 0. Then y is equal to c1 y1 of t plus c2 y2 of t includes every possible solution of the so really what this means is to any IVP, if and only if there exists a T0 where W of y1 and y2 is not equal to 0. So essentially what I'm saying here is you gain control over all possible solutions to for all possible IVPs, as long as you have two functions whose Wronskian is not just not 0 at some point, but not identically 0, not the 0 function. Or maybe in layman's terms, if W of y1 and y2 is not the 0 function, then y1 and y2 then give you all possible solutions via linear combinations. So this is just a little slightly different from what we were discussing before, but what we're gaining from this intuition is that if you're trying to find general solutions to second-order linear IVPs, you need to find two solutions whose Wronskian is not the 0 function. As long as their Wronskian is not the 0 function, then you're set. And you gain all of the control you could possibly wish for by taking linear combinations of those two solutions. Is this okay? Just the statement of this theorem?
Yeah, that's all good.
Great. So let's take a proof. So first, let phi be a solution. So in this case, what I mean is that I want L of phi to be equal to 0. And let the Wronskian of y1 and y2 at time t0 to not be 0. So here I'm just asking for one place where the Wronskian is not 0. As long as there's one place where the Wronskian is not 0, then I can do the following. So consider the IVP given by L of y is equal to 0, and y0 is equal to phi of t0, and y prime of 0 is equal to phi prime of t0. So essentially what I'm getting here is I'm saying, if the Wronskian is ever not 0 at some point, then I take my solution phi, and I find the initial data associated to phi at that t0. You see that that's what I've kind of done here? Okay. What I want to show is I want to show that phi, or phi, is equal to c1y1 plus c2y2, or choices of c1 and c2. Do we see what I'm doing here? I'm taking some place where the Wronskian is not 0. I'm taking a solution to my differential equation, and I'm finding the initial data associated to that solution at that point. And what I'm going to show is that phi is actually of this form, a linear combination of y1 and y2. We okay? So essentially, phi is a solution to this IVP because we define this IVP around phi. So of course, phi is a solution to this IVP. Moreover, by our theorem on the Wronskian, namely that if the Wronskian is not 0 at t0, then we can find solutions in terms of c1 and c2. Since w of y1, y2, t0 is not equal to 0, we can find y is equal to c1 y1 plus c2 y2, satisfying the IVP. Because whether or not we can find a solution which satisfies some initial data at t0 exactly depends on whether or not the Wronskian is 0 at that point. Okay, so now I've got one solution to the IVP phi and one solution to the IVP c1y1 plus c2y2. What can I say? I've got two different solutions to the same IVP. I think I'm going to interpret this silence as y'all being a little confused. Is that correct? Does anyone have a question here?
So if they're the same solution, does it mean they're equal then?
Yes. So what I can now write is by the uniqueness part, of existence and uniqueness of solutions to IVPs, I've got phi, which is a solution to the IVP, and I've got c1y1 plus c2, which is a solution to the IVP. By the uniqueness, phi must be equal to c1y1 plus c2y2, which is what I was trying to show. Or at least this is half of what I was trying to show. So I took some IVP associated to this data. I picked one solution phi, which to some initial data. I built the initial data around phi, and then I said, can I build a C1Y1, C2Y2 that also satisfies this initial data? And the moment that I can, the existence and uniqueness theorem tells me that those have to be the same function. So that means this phi lives inside my family of functions. There's the other direction to this theorem. If W of y1 and y2 is equal to 0, if the Wronskian is the 0 function, then for any t0, pick y0 being equal to y of t0 and y0 prime being equal to y prime of t0. We can always find, we can pick this data such that this initial data cannot be satisfied by any C1y1 plus C2y2. Essentially, if the Wronskian is 0 everywhere, then I'm saying pick any point t0, then these vectors given by y1 t0 and y1 prime t0 and y2 t0, y2 prime t0 live on the same line. And as long as you pick some initial data that's off of that line, you will never be able to satisfy this linear system. Or in other words, you can't satisfy this IVP at this point using this data, using any possible linear combination of y1 and y2. So the point is, to gain general solutions, find y1 and y2 such that the Wronskian of y1 and y2 is not the 0 function. It can be 0 in some places. It just has to not be 0 everywhere. And then your y1 and y2 give you all possible solutions by taking linear combinations. How are we doing here? Is this okay? Everyone just sleeping?
I think it's sinking in.
Slowly sinking in. Okay, yeah. It's true that we should probably do some examples because this all feels a little abstract. So let me do the following example.
What's the word before general up there?
Could you say that again? Sorry.
What's the word before general, like near the stars?
To gain. So if you want to write a general solution, if you want to have some compact way of writing every possible solution to any IVP associated with a differential equation, you need a pair of functions such that their Wronskian is not always 0.
Okay, thank you.
So as an example, assume that e to the r1t and e to the r2t are solutions to a differential equation. To really hear what I mean is a linear second order homogeneous differential equation. Assume, moreover, that R1 is not equal to R2. So in other words, I'm putting us back into the situation that we discussed on Tuesday, where the characteristic polynomial has two distinct real roots. Show that any possible solution to any IVP can be written. IVP, here what I mean is you fix the differential equation and you're changing the initial data. So I'll write that. Fix L, vary initial data. Can be expressed as y is equal to c1 e to the r1t plus c2 e to the r2t. So can someone tell me what you should be checking? I didn't catch that, sorry.
I want to check the Wronskian of e to the r1t and e to the r2t.
Exactly. What you should be checking is the Wronskian of these two functions identically equal to 0, or is it not 0 for some value of t? Okay, so essentially what we're being asked to compute is w of e to the r1t, e to the r2t, which is equal to the determinant of e to the r1t, r1 e to the r1t, versus, and then the second column is e to the r2t, r2 e to the r2t. What's the determinant of this matrix?
R2 e to the R1 plus R2 times t.
I'll write exactly what you were saying, but in a slightly more compact form. R2 minus R1 e to the R1 plus R2 t, right? Do we agree that this is the determinant if we factor?
Yeah.
Okay. We assumed that R1 is not equal to R2, so is this 0?
No.
Not 0. Since this is not 0, this function is not the 0 function. And if the Wronskian is not the 0 function, then every solution is a linear combination of the two solutions that you started. So all we needed to check in order to see that any possible solution to any IVP to this fixed differential equation that's solved by these two solutions, just need to check the Wronskian. The Wronskian is not the zero function, so any possible solution can be written as a linear combination. Any questions here? Okay, well, there are 40 people in the class and 21 people participating right now, which makes me a little sad. That's okay. That's all for today, and I hope you all stay safe during this time of the summer. Please take care of yourselves, and I'll chat with you tomorrow. Have a nice afternoon.
Thank you.
Thank you.
Thank you.
Thank you.